Problem 18 is a HNMR problem here. We're given the molecular formula on this one here, C8H6O2, which conforms to all of them here, and we just have to figure out which is the correct isomer, constitutional isomer here of that molecular formula. Here, the best advice here is, of course, to look at the number of signals first. Here we go through our list of things that we need to look at. Number of signals is usually the easiest thing, so I jump on that. Integration is the number of H's in short. That's not provided in this problem. On 3, we have the actual chemical shift here. That's somewhat difficult because you have to have memorized those numbers. And 4 here is usually the most difficult, the splitting. Okay, so let's go through here, number of signals. If you're wondering what these are, I've actually provided those because the splitting was important on this, and I wanted to make sure you knew what it was. So singlet, singlet, doublet, triplet here, and there's a little bit of complex splitting in here. That's why I provided. Let's just look at this as a doublet and look at this as a singlet, even though there may be some more complex splitting with that one. But here, let's look at the number of signals. We got 1, 2, 3, 4, 4 signals here. So we can go through and eliminate some of these here. Let's see here, and this is HNMR, so we're only looking at the H's here on this one. Over here we've got 1, 2, 3, 4. This side of the ring is the same as that side of the ring over there. That would be a possibility there. We have an H here, that's an aldehyde there. 1, 2, and then we have so much symmetry in this ring. There's free rotation around these single bonds right here, so this oxygen can freely move around, and this oxygen can freely move around like that. So this whole ring is going to be 2, and this is another repeat one on that aldehyde of 1. So only 2 signals with that. We can eliminate that one at this point. Here you see is the answer. Right here we got 1, 2, 3, 4. Don't know quite yet why that's the answer. More on that in a minute. Here we have a hydrogen here. 1, 2, 3, 4, 5, 6. That one there is definitely not the answer based on just the signals. Okay, so here at this point it's between these two here. We don't have integration. The next useful thing is going to be the chemical shift, and we can look at the splitting at the same time, but let's see here the chemical shift. Let's look at that peak. That peak there at around 10 is a higher aldehyde peak right there. That's the, let me draw this one out. That's the hydrogen right there on the aldehyde. Over here we do not have an aldehyde, we have an ester. That thing right here is an ester. So all we'll see with this is this at around 2 ppm for that one. That's the only thing that you're going to see for that one, not something at 10. But okay, say you missed that. Let's look at the splitting patterns here. We have a singlet, which if you didn't memorize the numbers, maybe you thought it was that one. There we have a doublet because, draw those in. We look to its neighbor right here for the n+1 rule here, where that is equal to 1 + 1. And then right here, this hydrogen is between these two hydrogens, so the n+1 here is equal to 2 + 1. That's going to be a triplet. And here, again, we'll have another triplet because this hydrogen is between the two H's right here. Okay, but these signals are the same as that one. This one is the same as that one over there. So, but this one is going to be N plus 1, 2 plus 1 there because of the two hydrogens right here. Okay, so let me write the codes here. We got triplet, triplet, doublet. So what we see over here, we don't see the two triplets. We see one triplet, one doublet, and a singlet. So we could have used 3 and 4 both to eliminate A right there. Let me actually do the peak assignments here for C2. This one here, this H on 2 would have been a singlet because it has no hydrogens right next to it. This one would be a singlet. That one right there is a singlet, singlet. Here we have a doublet because it is by this hydrogen right here on 4. Okay, and then that one right in the middle is between two hydrogens, so that would be a triplet. N plus 1 is 2 plus 1, a triplet is the code for that. So we do see the singlet, singlet, doublet, triplet, and that's the pattern in there. That's kind of the reasoning you would use to reason through NMR too. We can use 1 through 4, look at everything if it is necessary on a very complex one. Okay, on to the reactions now. Here we have our first reaction on number 19. HBr is reacting with this diene here that is unsymmetrical at 50 degrees, so it would be thermodynamic if it's possible. Let me sketch out this mechanism. Okay, make sure that's right, yep. So what we do here in reasoning this out, we want to first react the pi bond that leads to the most stable carbocation. That is this one right here. And remember, the two inside carbons, which should be position 2 and 3 here, are the ones that are always going to have the carbocation. That's where the carbocation is going to result. Okay. This one we can see is tertiary, and with the resonance form here, this is how we do the resonance. We have a secondary over here, so that's why that's the most stable one to react. If I reacted at this one right here, it would be a secondary from this one, and then the carbocation would also end up over here on this carbon, which is also a secondary. So this one has a tertiary that's dramatically better. The next thing here is our condition of around 50 degrees. That is a thermodynamic, and when we look at thermo, we're looking for the most stable double bond here. So what we have to do is compare this double bond to that, and we have 1, 2, 3 alkyl groups around this thing here versus this half, or this half of the ring. This is di-substituted, this one's tri-substituted. So this one is the more stable one, the tri. That means the bromine will end up going onto that carbon there, and there's the mechanism. For that reaction. Sometimes you can see on this one the picture's been moved around. Can't always guarantee that we're going to have the same picture drawn here, so we have to kind of compare, is that in the right spot? What I'm looking at is this methyl group here, which is attached to the double bond, is on the opposite side of the ring is that bromine right there. Okay. And here interspaced between these is the classification of the aromatic compounds. This one is a challenge one. We've got an oxygen here and an oxygen here, sandwiched in between boron. Boron here has a group 3. It belongs to group 3, so that means it has 3 valence electrons. And those 3 valence electrons here are used in these bonds. You have to go back to review Lewis structures to know that. But since it is in a 2p region of the periodic table that you got from Gen Chem, we do have p orbitals on this thing. And the boron then has an empty p orbital present. It has 1, 2, 3 electron clouds around it. sp2 hybridized with an unhybridized p orbital that is empty, no electrons in it. So since we have a sp2 hybridized atom beside these oxygens which have lone pairs, it will convert these oxygens to an sp2 atom. So here's the resonance for that. Only one lone pair is going to be counted towards Huckel's rule, because once we have the resonance form for this, let's just draw it out here. This is one resonance structure with one oxygen. Here, this is going to have a +1 charge on it. When oxygen has 3 bonds on it, it is plus charge. It's not going to donate another lone pair right here to something else to become +2. That's just too unstable. So anyway, we go back to counting then. Oh, let me finish here. Because this is sp2 and this is sp2, all these are sp2. There we have a ring that's completely conjugated. Okay, and then we count finally Huckel's rule, 4n plus 2. We got 2, 4 pi electrons then. That does not conform. So in other words, there's no way you can get this formula to make this match where this is equal. Okay, this mostly follows this. Oh, and you do have to use whole numbers here. So this follows the 4n rule. 4n then is the criteria for anti-aromatic